Hello, welcome to the new video of Math-S400, Mathematics and Economic Modeling. Today we're going to see an application of Brouwer's 6-point theorem to general equilibrium in an exchange economy. So we're going to look at a very simple model of a general equilibrium. This is going to be an exchange economy. So what do we mean by exchange economy? It means that we have a number of people in our economy. We can call them consumers, and there's not going to be any production, simply that everybody in the economy is going to have some bundle of goods, and we're going to allow the people to exchange goods between each other. Okay, and then the question is, will there arise something like a price out of this exchange economy? Okay, so maybe it's easier if I start by introducing some concepts and notation. So we're going to look at, we're going to need to have some consumers, and we're going to put them in a set N. Okay, so you have consumer 1, consumer 2, and so on until, well, this is the number of consumers. Okay, so we're going to denote them by 1, 2, 3, and so on. And we're also going to have some goods. Okay, and I'm going to assume that there are k goods in total. Okay, so a bundle, like we have seen before, a bundle is just an element in Rk. Okay, and we can make it Rk plus if you assume that people do not have or consume or buy negative amounts. Okay. So what do we have in our economy? Well, we have n consumers, and every one of these consumers will have a utility function. So the utility function of consumer j, okay, so j is here one of the consumers. So we're going to use a superscript to denote the consumer. Okay, so we assume that he will consume a bundle in Rk plus, and then this will give you a number. Okay, so these are the utility function. So every consumer has a utility function. So what are we going to assume? We're going to assume that these utility functions satisfy some properties. So first of all, we're going to assume continuity. Okay, then we're also going to assume strict quasi-concavity. So if you don't remember what strict quasi-concavity is, please look again to the lecture on convexity and concavity for the exact definition. And then we're going to assume a third property, and this third property is called local non-satiation. Okay, I haven't defined this property yet, so maybe I can do this first. So what is it? When is a utility function locally non-satiated? Well, if for every bundle Q and R k plus, and for every epsilon bigger than 0, I can find another bundle. So let me call this the bundle Z. So these are bundles in the ball of radius epsilon around Q, such that utility at Z is strictly bigger than the utility at Q. Okay, so this follows. So for example, if I have two goods, then for any bundle Q that I can find, and here I have to make an adjustment. So this is not the ball of radius epsilon, but it's the ball of radius epsilon, which is also in R k plus, right? Sorry. So I will show you in a minute what's the distinction. Okay, so we have a Q, and for every epsilon, I can look at the ball of radius epsilon around Q. Okay, like this, and then it has to be that there's at least one bundle in this ball of radius epsilon. I don't know which one, so maybe it's this one here. And this bundle has a higher utility than Q. Okay, so why do I look at intersection Rk plus? So for example, if this is my bundle Q, then I can draw the ball of radius epsilon. For any epsilon, I can draw a ball of radius epsilon around. And then here in this area here, this is this intersection, right? I should be able to find something. There should be a z here, such that let me write it here. So there should be a z in this intersection here that has a higher utility than q. So what's the intuitive meaning? Well, the intuitive meaning is that for any q, I can move an arbitrary small epsilon far away and be better off in some direction around q. Okay, so there's something arbitrarily close by that's strictly better. Okay, so this is why it's called non-satiation. Local, because it holds for every epsilon, and non-satiation means that you're never happy. You can always improve in some direction to be better off. Okay, so these are the properties that we're going to assume. So I lost my camera again. So you have consumers, everybody has utility function, and then we have a last ingredient, and that's an endowment. So remember, we're looking at an economy where people can exchange goods with each other. So in order to be able to exchange something, you have to have something, right? And what you have at the start, this is what I'm going to call the endowment, okay? And the endowment is simply a non-negative bundle, and we will assume that it's strictly, it cannot be equal to the origin 0, right? If your endowment would be 0, then you will not be able to buy anything, right? So it's a bit boring. So you assume at least you have something for some goods. Okay, so you can make an exchange to something else, or you can consume it, of course. Okay, so given all this, we can summarize this. Okay, so an economy consists of a set of consumers. Then for every consumer, we have a utility function, u of j, for all consumers j and n. And we have a set of endowments, ej, also for j. Okay, set of consumers for every consumer utility function that satisfies these three properties. And then for every consumer, also an endowment that's a non-zero bundle that this consumer can exchange. Okay, let's start with an economy of consumers, utility functions, and endowments. Okay, so let's assume that there's some price vector. So every consumer can go to the market and can sell some of its endowments and can buy other goods on the market. And the price at which the consumer can sell and buy stuff, let's call this the price vector P. Okay, so we assume that P is an RK++, right? So every good has a strict positive price. So if the consumer goes on the market and sells this entire endowment, of course, the amount of money that this consumer will get will be the dot product between P and EJ. Okay, so this is the bundle, right? So it's a vector of amounts. You multiply every amount by the corresponding price. So this is the total money obtained by selling EG. And then, of course, the consumer wants to buy something to consume, right? Let's call this the bundle Q, as we always do. And of course, in order to buy this bundle Q, it has to pay the price P. So this is the total amount that the consumer spends on the market. So total amount spent. Let me call this the total expenditure on the market. Okay, so it goes on the market. This is what the consumer buys, and this is what it sells. Of course, the consumer has no money to start with; it only has his or her endowment. So we need that this is less or equal to this. Okay. So we see that this is very similar to what we had before in the standard consumer model, except that here instead of this we had M, which was the total amount of money available to the consumer. Well, now we just substitute it by this number here. Okay, so if you look at all the bundles Q in RK plus, such that P times Q is less or equal to P times EG, well, these are all the bundles that the consumer can buy given this endowment and the price. Okay, so this is the budget set of the consumer, and we can parameterize this as a correspondence, right? And you would use the price P. So in particular, we will assume that this here is fixed, right? So normally we should write this as a correspondence of prices and endowments. For simplicity here, we just keep the endowments fixed and only look at this as a correspondence of a price. Okay, so this is a correspondence that goes from RK++, right, the set of all the prices, and it gives you a subset of bundles that you can buy to RK+. Okay, so this is the budget correspondence. Okay, so if I draw the picture in 2D, so we have our endowment, that's some vector in the space, and then you have a price, right? So if I draw the line with slope P through this vector here, then this will be my budget. Okay, so we see that if prices change, so normally if you have two goods, right, let this be good 1 and this be good 2. So normally if the price of good 1 increases, what happens is that the budget line rotates inwards, right? Good 1 becomes more expensive, so you can buy less of good 1, but you can still buy the same amount of good 2. So here, if you have a model with an endowment, this is no longer the case, right? So if the price of good 1 increases, you will also rotate this budget line, but now you will rotate through this endowment, right? Because you can always buy your endowment, so your endowment should always be on the budget line. Okay, so you get a rotation through the endowment. So why is this? Well, in some case, because all the goods one that are in your endowment, you can sell them at a higher price, so at some cases you also have a higher amount of income. Okay? So this is just to make clear that this model, so this would be a model where your budget depends on the price and total amount of income. So here we have this budget here where you have an endowment, right? So it's a little bit different than we have seen previously, but it's still fairly similar. So then if we have a consumer with this kind of budget, and our consumer has a utility function, so we can write down the problem of consumer J, right? That's to maximize this utility function uj q, subject to q is in the budget set with some given prices p. Okay, this is the problem of consumer J. Okay, so what do we know? Well, we know that this is continuous. This is also strictly quasi-concave. This here, this is this budget set here. Well, previously we looked at this budgets and we have shown that it's upper and lower hemi-continuous and it's also convex valued. Well, you can do a similar thing here, and then actually you can show, I will not do it here, but it's a good exercise to show that this is upper hemi-continuous, lower hemi-continuous, and convex valued. Okay, so if I solve this problem, well, then I will get an optimal value function, which now depends on the price, right? Because this depends on the price. So this is similar to what we have seen before. This is the indirect utility function. And then we have a optimal solution correspondence. Which we know, so this one is here, indirect utility function is continuous. Okay, so this follows by Burgers' maximization theorem. The optimal solution correspondence will be upper Rahimi continuous, also by Burgers' maximization theorem, right? Because all the conditions are satisfied. Also because this is strictly quasi-concave, you have seen in the section on quasi-concavity that this is single-valued. Okay, so this correspondence only contains a single bundle, right? The optimal bundle at this particular price. So in particular, if we only select this single bundle, then we get a function. For every price, we get a different optimal bundle. Okay. So let us write this as qg of pi, right? So this is this contains a single element, and this is the element that the set contains. Okay, so this will be the demand function. And because this is upper Rahimi continuous, we know that this demand function is continuous. Okay, it's one of the exercises on the section, I think, on correspondences, that if a correspondence is upper Rahimi continuous and there's only a single element, then this element will make a function, and this will be a continuous function. Right. So if you don't remember, have a look back. So this is a part where all the previous lectures somehow come together to get to all these results. Right. So this is something that you will work with in the following part of this lecture. Okay. So for the following part of lecture, we will also need an additional result. So let me call this the lemma. So if this function, remember, the utility function of consumer j goes from rk plus to r, is locally non-satiated. Okay. Well, you can look at this optimization problem, right? So we also assume, of course, that it's continuous and strictly quasi-concave. Okay, so we can look at this problem, we can solve it. Then we get an optimal demand function. Well, let's show that if we multiply this bundle here by the corresponding prices, well, then what we will get is that this is equal to P times EG. Okay, so what's the intuition behind this result? Well, we know that the optimal bundle should be in the budget set, right? And remember that this is the set of all bundles such that P times Q is less or equal to P times EG. Well, this lemma says that if this under local non-satiation, this in fact will be inequality at the optimal bundle, right? So at the optimal bundle, you will never consume inside the, you can call this the interior of the budget line. Okay, so if this isn't your endowment, then it's impossible that your Q is inside, right? So the optimal bundle should be on this on the budget line here, right? You cannot consume inside the budget set. Okay, so that's what the lemma says. It has to satisfy this property. Okay, so let's prove this lemma. So what's the idea? Well, the idea is to make a proof by contradiction. So what we're going to do is we're going to assume that this inequality doesn't hold, right? Then because we have this weak inequality. This inequality has to be strict. If this is not an equality, then it has to be a strict inequality, which means that Q is inside this budget set, right? So we have a case like this. Okay, then what can we do? Well, we can always find an epsilon such that this ball is somehow inside this entire budget set, right? And then by locally non-satiation, we can find a Z somewhere in this ball here that's strictly better than Q. Okay. However, if let me call this the Z here, right? However, if I have a Z that's strictly better than Q, and it's in the budget, then of course Q cannot be the optimizing bundle, right? Because we derived this from the utility maximization model. So this will get our contradiction. Okay, so let's make this a bit more formal. So proof, so assume, so this is a proof by contradiction. Okay, so assume that P times the optimal demand, I should not write the bar here because it's a function, right? So let me write it like this, is strictly less than P times EG. Okay, so that's my contradiction, because remember, if this is not an equality, then because it's still, this is the optimal bundle, so it has to be in the budget set. So we need to have a weak inequality here. It's not an equality, so it has to be a strict inequality. Okay, so this is my assumption. Okay, so by local non-satiation, well, I know that for all epsilon bigger than 0, there exists the Z in B epsilon Qj intersection Rk plus, such that U of Z is strictly better, Uj of Z is strictly better than Uj of Q. Okay, so this is what we're going to use. So we're going to pick a particular value of epsilon for which this holds, right? Well, let's just skip some steps here, and then we're going to fill in this value of epsilon that we would like to use. Okay, so what do we want this Z to satisfy? Well, we want this Z to satisfy that it's inside the budget set, right? So we want that the fact that Z is inside the budget set, this can be rewritten as P times Z is less or equal to P times EG, right? Because this exactly defines what the budget set is about, right? So we need to find an epsilon. Okay, so such that this Z satisfies this condition. Okay, so let's start with P times Z on one hand, and then we would like to get some inequalities here, and then in the end arrive at this value here. Okay, so we don't know P times Z, but we know that Qj or Z is epsilon close to Qj, and Qj is in the budget set. Okay, so how do we get Qj in here? Well, we can add P times Qj and then subtract P times Qj, right? So I always forget no line here because it's a function. Okay, so now let's take this one and this one together. So now we have P times Z minus Qj, and then we have plus P times Qjp, right? So this is just bringing this and this together in this first term here. Okay, so here we have the dot product P times this. So we know that this is less or equal to the absolute value of P times Z minus Qjp plus P times Q JP. Okay, so this is the dot, this is a vector here. This is a vector. We have the dot product of two vectors, the absolute value. So we can use the Cauchy-Schwarz inequality. So this is less or equal to the norm of P times the norm of Z minus Q JP. Okay, and then plus the last term here. Okay, and then because we assume that Z was in the ball with radius epsilon around Q, okay, we know that this is smaller than epsilon. Okay, so this is smaller than P times epsilon plus P times QJ P. Okay, so let's look at this here. What do we know? Well, we know that this is smaller than this. Okay, so take so this, let's use a similar trick as before. This is P times EJ plus P times QJP minus P times EJ. Okay, so here I added, here I've subtracted the same thing, right? So this is 0, and this is simply repeating this thing here. So what do we want in the end? In the end, we want P times Z to be smaller than P times EJ. So I started with P times Z here, and here I have P times EJ. Okay, and I would like this to be smaller than P times EJ. So I can do this if what remains here, what remains has to be smaller or equal to 0, right? If this entire thing here, so this first term and this term, is smaller or equal to 0, then this will be less or equal to this. Okay, and how can we guarantee that this is true? Well, we just take epsilon on one side and then put everything else here on the other side. So here we have P times EG minus P times QJ P, and we divide it by the norm of P. So we take epsilon to be smaller or equal to this value here. Okay, so what can we do? Well, this holds for every epsilon. So take epsilon to be equal to this expression over here, which we know will work. Right, so this is P times EJ minus P times QJ P divided by P. And what do we have? Well, we have that this is strictly bigger than this, right? So this is strictly positive. The norm of P is in RK++, so it's also strictly positive. So we know that this is strictly positive. So this is indeed a value, a good value for epsilon, right? This is allowed value for epsilon. So if we take this one here, then we know that there exists a Z, right? And this P of Z is lower or equal to P times EG. So from this derivation, it follows that Z is feasible, and the utility of Z is greater or equal to the utility of QJ, right? This follows from here. And this is a contradiction because this bundle was assumed to be optimal in the budget set, right? The utility maximizing, and we have found something that's strictly better. All right, so this is a contradiction by the definition of QJ of P. So this shows that indeed, if you have local non-satiation, then at the optimum, the budget constraint has to hold. Okay, so let's recall what we have so far. We had a consumer that maximizes his utility, subject to Q is in the budget set at some price. We haven't talked about prices yet, but for now, take the price fixed. So if you do this, so something that I forgot to tell you, well, in fact, this is just a detail. But if I define the budget set, well, actually this depends on the endowment. So you can say the budget set for different people is different, right? Because the endowment will be different, this will be a different budget set. So we can also put a superscript at the budget set here to make sure that indeed this budget set will vary from individual to individual. Okay, so I solve this, every consumer solves this problem, the budget maximization problem. We have an optimal demand function Qj of P, and we know that if we multiply this together, well, we get exactly P times the endowment, right? So the consumer spends his entire amount of money on the consumption. Okay. So we're going to define a new object now, and this is going to be the excess demand function. Okay, so this is what the consumer buys, right? This is a vector, and this is what the consumer has. Okay, so we're going to take the difference between these two things. So this is a vector, this is a vector, so what comes out of it will be a vector. Okay, so we have an entry for the first good, an entry for the second good, an entry for the third good, and so on. Okay, so this would be a vector. So if this would be positive, okay, then what the consumer consumes of the first good is higher than what the consumer has of the first good to start with. Okay, so if this is positive, then we say there's excess demand for the first good for this consumer. On the other hand, for example, the entry of the second good is negative, then here this for the second good will be smaller than the endowment, so there's negative excess demand, right? The consumer has more than he consumes of the good, so he will be a net seller of the good, right? So maybe this is the right way to say it. If it's negative, then consumer will sell more than he buys, right? So he's a net seller. If it's positive, then he's a net buyer of the good, right? So he buys more of the good than he actually has, so he has to purchase an additional amount on the market. Okay, so this is the excess demand function for consumer J. Okay, so what can we do now? Well, we can sum over all consumers their excess demand functions. Okay, so for the first good, we look at all the net demands or net supplies, and we sum them all together over all the consumers. Okay, so this is the, you can call this the aggregate excess demand. Right, so it's the total amount of a particular good that is consumed minus the total amount of this particular good that's offered on the market, right? Total endowment of this good. So total demand minus total supply. Right, so this is why it's called an excess demand. You look at all the amounts that are bought of the good and then all the amounts that are supplied of the same good. Do this for every good, you have a vector, and this will be the vector. Okay, and we're going to use a special notation for this. We will call this vector z p because it's a function of p, right? So for different prices, you will have a different demand function of the different consumers. So you will have a different excess demand function also. So this is z of p. Okay, so z will be a function, it will go from rk plus plus, right? So it will take a price and it will produce a vector in rk, right? And some of its elements can be positive, right? If the total demand is bigger than the total supply, it will be positive. If the total demand is less than the total supply, it will be negative. Okay, so if zp, can look at this one. If I look at good I, right, so let me use subscripts for the goods, then demand good I is bigger than supply good I. Okay, so if ZIP, so this if it's positive. If it's negative, well then the demand good I is less than the supply good I. Okay, so if you have a market and you have a pricing system, right, so you can intuitively see that this will not be in equilibrium, right? If there's more demand than supply, then the prices should adjust, right? This is how the market works, right? If it's negative, then there's more supply than demand, so the prices should also adjust, right? So P is in equilibrium. Price vector if for all goods that IP is equal to 0. Okay, so this means that aggregate demand is equal to aggregate supply, but we will make a small adjustment, right? So we say or ZIP is negative, right? There's more supply than demand, but in this case the price of good I has to be 0, right? So there can be more supply than demand, but if there's more supply than demand, then you're basically making the good free, right? Nobody wants to consume it anymore, right? So then we allow for excess supply. Okay, so in the remaining part of this lecture I will show that given all the conditions that we have stated before, there's at least one equilibrium price vector, right? So there's a price vector P such that at this particular price vector aggregate demand is equal to aggregate supply, except for this strange case, you may say. So before I give the proof of the existence of an equilibrium price, I will first state some properties of the excess demand functions. So properties of the function, the excess demand function ZP. So the first property is that if so this is a vector of excess demands, excess supplies. If I multiply this vector by the price, what I get is 0. Okay, and I should be, and this holds for every price. Right, not only for the equilibrium price, but for any price vector P. If I multiply the excess demand function by the price vector P, I get the number 0. Okay, so this is a dot product, so it gives me a number. So the proof, in order to see that this is true, it's not overly difficult. So I have P times Z of P. Well, this is equal to P times, this is the excess demand, right? So it's the sum over all consumers of the demand function of the consumer J minus the endowment of consumer J. Okay, so this is the dot product of P times a sum of vectors. So you can show that this is equal to the sum of the dot product of P with each of these vectors, right? So this is Q JP minus EJ. Okay, so and this is equal to J equal to 1 to N of P times QJ of P minus P times the endowment. Okay, and this, because we have local non-satiation of the utility function, this is equal to 0, right? Remember, the lemma that you have proven is that the optimal bundle will be on the budget line, so this would be equal to 0. So here we're summing a number of zeros, so this would be indeed be equal to 0. Okay, so we have this identity here. So this follows from budget, from consuming budget line. Every consumer consumes on his budget line, so this identity holds, right? And this identity has a special name, so this is called Walras law, right? It's the law of Walras who put this forward, so this is called Walras law. Okay, so a second property is if I take a number lambda bigger than 0 and I multiply all the prices by lambda. Okay, so this is this is a vector, this is a number, I multiply every entry in this vector by lambda, right? This is a number multiplied by a vector and I plug it into the function z. Okay, so what happens then? Well, that's a good question, of course. So let's have a look back to the utility maximization problem of every consumer, right? So every consumer maximizes UJQ subject to Q in the budget set, right? And remember, the budget set was all the bundles Q and RK plus such that P times Q is less or equal to P times EG. Okay, but now I'm looking at the problem where all prices are multiplied by some number alpha. Okay, so what changes when I do this for this maximization problem? Well, I have to look at the budget set where all the prices are multiplied by some number lambda. Okay, so if I do this here in the budget set, I have to multiply these prices by some number lambda, and I have to multiply these prices by some number lambda, right? So these are the same price vector. And I see that actually when I do this, I can delete them both, right? So in some sense, it doesn't matter if I multiply all prices by the same number, I get entirely the same budget set. Okay, so in particular Bj, if I multiply every price by the number lambda, the budget set remains the same. So if the budget set remains the same, then of course the optimal solution of this problem will also remain the same, right? So the optimal bundle demanded at these prices will be the same as the optimal bundle demanded at these prices. Okay, so what happens here if I multiply all prices by lambda? Well, then the total amount of money that I can get by selling my endowments is lambda times bigger. However, everything I buy is also lambda times more expensive. So if all the prices increase by the same amount, I'm the same amount more rich than I have to spend, so this doesn't change anything. So you can call this there's no money illusion, right? So if all prices increase by the same amount, basically what you have is inflation, but if everything increases by the same amount, you're as rich or as poor as you used to be beforehand, so nothing changes in real terms. So also the excess demand function will not change, right? Because here everything remains the same, and the excess demand function is just the sum of these here. There's no p here. So if I multiply this by lambda, nothing changes because of this. So the excess demand function will also not change. Okay, so this is the second thing. And then the third property is that ZP is continuous. Continuity is easily seen. This ZP is a sum of excess demand functions. Each one of these is continuous, right, by Burgess maximization theorem. So you sum over a number of continuous functions, so this will also be continuous. Okay, so let me come back to the second property here. Well, this means actually that we can multiply all prices by some number and remain at the same problem, right? So we're going to use a special kind of number here, right? So we're going to set lambda to be equal to the sum over all goods of the price pi. Okay, so if I do this, I have ZP will be equal to ZP divided by the sum over all prices. Okay, so what I can do is I can define this to be a new kind of price, a normalized price, right? So let me call this p tilde is equal to the vector p divided by the sum of all prices, right? So just by substitution, this is equal to zp, right? So this is the vector of all prices normalized by the sum of all prices, right? So if the price of good 1 is equal to 1, the price of good 2 is equal to 2, and the price of good 3 is equal to 3. So this is my p. What will be the normalized price? Well, I have to divide each price by the sum of all prices. So the sum is here 6. So price of good 1 will be 1 over 6. This will be 1 over 3, and this will be 1 over 2. Right? So this is how you can normalize prices. And instead of looking at z of a particular price, you can always normalize it, right? So the excess amount will not change, and look at z of these normalized prices. Okay. This is called normalization, right? So normally in economics you can do normalization in two kinds of ways. Either you can fix the price of one good equal to 1 or another value, or you can fix some function of the prices equal to 1 or some fixed value. So here we take which function do we take? Here we take the sum. Okay. So what do we know about this normalized price vector? Well, we know that if we add up all the elements in this normalized price vector, we get 1, right? So these are non-negative numbers and that add up to 1. So this is in the k-1 dimensional simplex, right? As you have seen before when discussing Brouwer's fixed point theorem, this is an element of the k-1 dimensional simplex. So previously we had z going from rk++ to rk. Okay. Now our function z, the domain, we will change it to delta k-1 to rk. Right, so how do we do this? If you have a price here, well, we first normalize it, then it's in delta k-1, so we can map it to rk. Alright, so this will be the standard point that we will use in order to prove the existence of an equilibrium. Okay, so let's go to our mean result theorem. So what do we have? We have an excess demand function z from delta k-1 to rk as an excess demand. So in particular it satisfies this property, right? You already used this one, okay, to normalize the prices, and it's continuous. Okay, so these are two properties that you will need. Then we can show that there's an equilibrium price vector, right? So there exists the P in RK plus such that for all goods I, either the excess demand is equal to 0, and if ZIP smaller than 0, then PI is equal to 0. Right, so that's why we take RK plus and not RK plus plus. Okay, so for all goods i's, the excess demand is equal to 0. If it's or, it's negative, but then the prices has to be equal to 0. Okay, so this is the theorem that we're going to prove. And it's good to have an intuition of how we are going to find this equilibrium price vector. So let's take a price vector and let's look at ZP, the excess demand, for a particular good I. So if this is strictly positive, then we know that demand is bigger than supply. Okay, and if demand is bigger than supply, then we would expect that the price for this particular good should go up. Okay, so Pi should increase. Okay, there's more demand than supply, price of good I goes up. If ZIP is smaller than 0, well, then we know that demand is smaller than supply. So Pi should decrease. Okay, which is basically the mirror image of this thing here. So what are we going to do? We're going to focus on this thing here. So we're going to look at all goods for which ZIP is bigger than 0. And then we're going to say, okay, the prices of these goods will increase. And then because we are normalizing prices, right? So we are dividing by the sum of all prices, then automatically all goods for which this is negative will decrease, right? So we only have to look at this one in order to get also intuitively the second thing working. So what are we going to do? We're going to start with the price, and we're going to adjust the prices looking at whether this is strictly positive or not. Okay, so if you want to look at whether this is condition is satisfied, what we can do is we can look at the maximum of ZIP and 0. Right, so if this maximum is bigger than 0, then this condition is satisfied because this is strictly positive. If this condition is not satisfied, then the maximum of these two things will be equal to 0, right? So this function maximum will be equal to 0. So we're going to use this, and we're going to call this gi of p, right? This is the function gi of p for good I. So gi of p, so if this is my z, something like this, right? It's going to look at the maximum of 0 and z, right? So it's going to be equal to z if zi is strictly positive, and it's going to be equal to 0 if this becomes negative. So what do we have? We have a price Pi, and then what we can say is, well, if this is strictly positive, then this will be positive. So the new price, maybe it could be this thing plus gi of p. Okay, so we start with a certain price, right? We look at whether the excess demand of this particular good is strictly positive. If it is, then we are going to increase this price. Okay, so new price good I could be something like this, right? It could be the old price plus something positive in case where the excess demand is strictly positive, right? When demand is bigger than supply. However, this thing does not satisfy the normalization constraint, right? It's not in delta k minus 1. So what do we need to do? Well, we need to divide it by the sum of all prices. So this will be the new price. What will be the sum of all new prices? So let me count over L. The price of good L plus the sum over L of G LP. Okay, so this is simply the sum of all these numerators over all the goods. Okay, so we're going to define the new price to be equal to this divided by this. Okay, and we know that because the price vector is in delta k plus minus 1, we know that this will be equal to 1. Okay, so this will be equal to Pi plus GIP divided by L PL plus L 1 plus sum over L of GL of P, right? So this is going to define our new price. So what we can do is we can define a function f from delta k minus 1 to delta k minus 1, right? So we're going to plug in a price vector, this one here, and f of p is going to give the new price of good I. Okay, so fp, the ith element of this vector f of p will be equal to pi plus gi of p divided by 1 plus lgl of p. Okay, so far so good. So this is going to be the price adjustment. If this is the old price, then this is going to make a new price for I. You do this for every good I, and you have the function f of p. Okay, so f is a function from delta k minus 1 to delta k minus 1, and this is continuous. Okay, so why do we know that this is continuous? Well, because this here is continuous. We know that gi is continuous. Then of course the sum of all the g's is continuous. So you have a continuous function divided by a continuous function. So this is indeed continuous. And now we're going to use Brouwer's fixed point theorem. It says that f has a fixed point. Okay, so in particular there's a price such that f of pi is equal to pi, right? This is the fixed point. Of course, this is a vector of pi's and this is a vector of fpi's, right? So this vector will be equal to this vector at the fixed point. And let me call this fixed point p star. So this is at p star. We have our fixed point price. So for all goods, you have that the p star of this good is equal to pi star plus gi at this p star divided by 1 plus gl p star. Okay, so what can we do with this equation? Well, we can bring this to the other side. And then you have this times 1 plus pi times l gl at p star is equal to pi star plus gi p. Okay, so here you can delete pi from both sides, which simplifies the equation a little bit. So what's the next step that we're going to do? We're going to multiply both sides by zi of p. Right, so the excess amount of good I at p star. So we're going to multiply this by this number. So this gives me zi p star, and then times pi star, and then times the sum of gl p star is equal to zi of p star times, these are two numbers which you multiply together. Okay, so we did this, and now we're going to sum over all goods I. So I equal to 1 to k of pi zi p, and this is a common term. This doesn't depend on I, right, because it's a sum over all goods. So we can take this outside the summation. gl p star is equal to the sum. So we summed this side, we also have to sum this side, I1 to k of zi p star gi p star. Okay, so let's have a closer look at this term. What's this? This is the price of good I divided by zi of p star, and then you sum over it. So you can recognize this as the inner product of p star and zi p. Okay, and we know that this is equal to 0 by Walras law. Okay, so this entire left hand side will be equal to 0, because here you have 0 multiplied by something 0. So if we rewrite this, we have that I1 to k of ZIP times GI of P, so this is all P star, will be equal to 0. Okay. So recall what this was. You have the sum from 1 to k of ZI P star of the maximum of 0 and ZI P star is equal to 0. Okay, and we're almost there. Trust me. So let's see what happens with all these terms and this term here, right? So this is the product of two numbers. So what if ZIP is strictly negative? So if demand is less than supply, well then this is strictly negative. This is also strictly negative, but you're taking the maximum of 0 and something strictly negative, so this will be 0. Right? So in this case, ZIP star times the maximum of 0 ZIP star will be equal to 0. Okay? If ZI of P star is greater or equal to 0, well then this is greater or equal to 0, and here you have the maximum of 0 and something greater or equal to 0, so this will also be greater or equal to 0. So you're multiplying two non-negative numbers together, so you get something that's non-negative. Right, so ZIP star times the maximum of 0 ZIP star is greater or equal to 0. So if this is negative or this is positive, this thing here will always be non-negative. Okay, so this, whatever the value of ZIP, this will be greater or equal to 0. So here you have a sum over k goods. Every term is greater or equal to 0, and the sum has to be equal to 0. So this can only happen if all these terms are equal to 0, right? Because if one of these terms will be strictly positive, then of course the sum should be strictly positive. Okay, so for all goods, it follows that ZIP star times the maximum of 0 and ZIP star should be equal to 0 for all goods I. Okay, why? Because they're always non-negative and they have to sum to 0, so every term has to be equal to 0. Now let's have a look at what happens if ZIP is strictly positive. Well, then we have something strictly positive here, and then we take the maximum of 0 and something strictly positive, so this will be strictly positive. Multiplying two strictly positive numbers together is strictly positive, so this condition is violated. Okay, so ZIP strictly bigger than 0 is not possible. Okay, what if ZIP okay, so from this it follows that ZIP star is less or equal to 0 for all goods I. Okay, so there's no excess demand. This is what it says. Okay. So what do we also know? We know by Walras law that P star times ZP star is equal to 0. Okay, so I can rewrite this as the sum over all goods of Pi star times ZIP star is equal to 0. I know that all the ZIP stars are less or equal to 0, right? So these are all less or equal to 0. All the Pi's are greater or equal to 0. Okay, and so this is a sum of non-positive numbers, right? They can be either negative or strictly negative, but they have to sum to 0, right? So this means that if ZIP star is strictly less than 0, well, because this has to add up to 0, so let me take a step back. Here, this is greater or equal to 0, this is less or equal to 0, so the product has to be less or equal to 0. But the sum has to be equal to 0. So similar to what we have seen here, right, the sum of non-negative terms that add up to 0. Here we have a sum of non-positive terms that add up to 0. So for all goods I, you have that Pi times ZIP is equal to 0. Every term has to be equal to 0. Okay, so if this is strictly negative, then because this product has to be equal to 0, then Pi star is equal to 0, right? And it's impossible that this is strictly positive, right? So either this holds or ZIP has to be equal to 0. Okay, so let me rewrite it. So we have that this product has to be equal to 0. So this can happen either if the second one is equal to 0, and if the second one is, or if the second one is not equal to 0, which means because it's not strictly positive that it has to be negative, well then Pi star is equal to 0. Okay, and this is what we needed to show in order to have an equilibrium price vector. So we made a somewhat long derivation, so let me try to go over it again. So we would like to show that there exists a price vector P, well, we can call it P star as we use in the proof, such that either for good the excess demand is equal to 0, or it's negative, but then the price P star has to be equal to 0. Okay, so how did we go? Well, we said intuitively if the demand is bigger than supply, then the price should increase, right? So we're going to make a function that takes prices to new prices, and we're going to increase the prices for all the goods that have an excess demand bigger than 0, right? So we define this function gi of p that takes the maximum of the excess demand for this good I and 0. And we're going to say, okay, what can we do? Well, we can take the price and then add gi to this price in order to get a new price. But in order to get a new price that is normalized, we have to divide it by the sum of all these new prices. And this is what we're doing here. Okay, and then we said, okay, the price is sum to 1, so we can substitute this for 1. So we define the new price as being f of the old price, right? So the new price is going to be Pi plus this jump here, divided or normalized. Okay, and then you said f goes from the k-1 dimensional simplex to the k-1 dimensional simplex, so it has a fixed point by Brouwer's fixed point theorem. So this fixed point satisfies this, and then the remainder of this theorem is simply rewriting this condition in a different way. So we first take this to the other side, then we get this expression here, then we multiply both sides for the good I by the excess demand Zi, right? This is this term here and this term here. Then we said we can sum this equation over all the goods. This is what we done here in this step. Then this first term here drops out because of Walras law, right? So this entire thing becomes 0. So we only are left with this part here that's equal to 0. Okay, so here we just rewrote gi using the definition of this thing. And we have shown that whatever the value of Zi, this term here will always be non-negative, right? It's greater or equal to 0. So a sum of non-negative terms that add up to 0, then every term has to be equal to 0. What is stated here. And then because every term here is equal to 0, we have seen that ZIP strictly positive is not possible, because otherwise this would be strictly positive, right? So for all goods we should have that the excess demand is less or equal to 0. And then we use Walras law once again. So price times excess demand is equal to 0. Because this cannot be strictly positive, it has to be less or equal to 0. This is greater or equal to 0. So we have a sum of non-positive terms that add up to 0. So every term has to be equal to 0. So this is equal to 0 whenever Zi P is equal to 0, or if it's negative, and remember it cannot be positive because this is what you have shown here, or if it's negative, then the first term has to be equal to 0. Okay, so that's the proof. So I would like to finish with the remark, and the remark is that the proof that we have just seen is not entirely correct. In particular, I cheated a little bit. Okay, let me first explain what the cheat is here. So the cheat is actually when looking at this normalization step here. Okay, so it's here. So the normalization is okay. I can divide by the sum of all prices. But then I said, okay, if I normalize this here, I'm changing my domain from rk++ to delta k minus 1. And remember, delta k minus 1 was the set of all vectors. I can now call them p in rk plus, such that the sum of all prices is equal to 1. Okay, so here I have strictly positive prices, and here I'm actually allowing some prices to be equal to 0. Okay, because otherwise, if I don't allow some prices to be equal to 0, then my domain is not the entire set delta k minus 1. And in particular, my set of the domain will not be closed, right? I leave out the points where some of the prices are equal to 0. And if I do this, well then basically this function will also not go from delta k minus 1, but it will go from this set without the zeros. So I cannot apply Brouwer's fixed point theorem. Okay, so this was the cheat that I did. So I was not entirely honest that this is actually the proof of an equilibrium. It's possible to fix the proof, but it's quite technical, and it doesn't really add to the argument here, or the intuition behind the proof, that it basically is using adjustment of prices towards by increasing prices for which the excess demand is bigger than the supply. Okay, so I'm going to leave it like this with the incorrect proof, but just if you were wondering why I suddenly switched the domain and that this is not entirely valid, you were entirely correct that it's not valid. So actually we have to modify the proof a little bit to make it valid. I will give in the notes some references. I think in the lecture notes you can also find a reference to the handbook that actually has a correct proof. It uses some epsilons and convergence of equilibrium prices to another equilibrium price and so on. So you can read it if you're really interested.